Yeah, right.
Right. This occultation light curve is typical of those involving faint main belt asteroids. And there are several salient features that I wish to point out. By the way, are you seeing my mouse?
Yep.
Yes.
Good. The first thing is that the disappearance and the reappearance are abrupt. As you know, any instantaneous change in brightness may involve a single frame of intermediate brightness if the change occurs during the exposure of that single frame. Thus, a single frame of intermediate brightness does not mean that the disappearance or reappearance is gradual. But in general, main belt asteroids have abrupt disappearances. Second, the brightness during the occultation is at the same brightness as the background sky. That is, it drops to 0 if the asteroid is faint. Third, the event bottom is flat. So those are like 3 main characteristics of asteroid light curves that we look for. These are the 3 positive chords of the first Apophis occultation at Oakdale, Louisiana that I showed you last time. I want you to notice that it appears that the brightness did not drop to 0 in any of these 3 events. They were quite short. This one seems to have a little spike in the middle. Actually, there may be a trace of a spike in the middle of that one. And this one is just remarkably far from the baseline, a single frame event. None of these looks like the previous light curve I showed you of a typical main belt asteroid occultation. About 10 years ago, Steve Conard recorded this light curve of an occultation by the Jupiter Trojan 911 Agamemnon. It shows a secondary event consistent with a small asteroidal moonlet. Note that the brightness of this secondary event does not drop to 0. That nadir right in there is not 0. And notice also that there are 3 frames of intermediate brightness. You can see them as fine little points there, which means that at least one of those events, the D or the R, was gradual. This light curve is an occultation by 3200 Phaethon. It was made by Miyoshi Ida on October 15, 2019, from a site near the predicted center line. The points along the red lines are the raw data, while the green lines are medians of unspecified sample length. The recording was made at 100 frames per second. It shows a spike in brightness in the middle of the event bottom. This is Kai Gatros light curve made on April 11th of 2021 of an Apophis event. It also is at 100 frames per second, so it's quite a brief event. It shows spikes in brightness immediately before and after the geometric, what seems to be the occultation. And notice the event bottom is rounded. So this light curve also is not like the typical main belt asteroid. There are 4 strange phenomena with very small asteroids. Incomplete disappearance of the star, brightness spikes immediately before and after the event, and also during the middle of the event, rounded event bottom, and multiple frames of intermediate brightness. I know of 3 causes of these phenomena. Firstly, Fresnel diffraction effects. Secondly, frame rate effects. And thirdly, effects of the subtended diameter of the star. I actually cannot read the top part of this slide because I have something in the way up there. But anyway, the accurate calculation of diffraction effects involves double integrals in the complex plane and Lamel function and Bessel functions, and therefore is beyond the capabilities of most amateur astronomers. Fortunately, a simplified understanding can be obtained by using the Fresnel length and an asteroid's radius together to compare an occultation event to a few published examples of expected diffraction effects. The Fresnel length has been defined in several ways in the astronomical literature, but for the purpose of this presentation, we'll calculate it the way it's most commonly calculated, and that is the square root of the quantity wavelength times distance divided by 2. If you do this type of calculation, you have to be careful with the units. The easiest way, I think, is to convert everything, both the wavelength of light and the distance, which we think of as astronomical units, convert them to meters, and then your Fresnel length will be in meters. Assuming that the star is a point source, when the asteroid's radius is much greater than the Fresnel length, diffraction effects will be negligible. When the asteroid's radius is approximately equal to the Fresnel length, diffraction effects will be very prominent. When the asteroid's radius is much smaller than the Fresnel length, diffraction effects will so scatter the light that the occultation may be undetectable. It thus may appear to be, quote, diffracted out, unquote. A convenient way to represent this is to divide the asteroid's radius by the Fresnel length. The resultant value is often called rho and is represented by the Greek letter itself, rho. So a value of rho of about 1 is associated with very prominent diffraction effects. This slide is very busy, but I'd like you to walk you through some of it because it is central to understanding the effects of diffraction in occultations. Let me ask you, are you able to see at the very top line where I've put 0.88 and 2.9 and 5.9? Can you see those numbers at the top?
Yes.
Okay, good. I ask because I can't see them because there are Zoom functional things up there that prevent me as host from seeing the very top of the slide. This figure is from a 1987 article about diffraction effects in occultations written by Rokes, Mansuke, and our associate Bruno Siccardi. I have added the rho values at the top of each column. So those numbers that at the very top of the rho values are the asteroid's radius divided by the Fresnel length, which I showed you how to calculate. The diagrams will apply to any occultation that has the same value of rho, which depends on wavelength, distance, and asteroidal radius. The diagrams are idealized by having been computed using a single wavelength and a star that is a point source. Notice the 4 drawings at the left edge of the diagram over here. These indicate the shape of the asteroid and the occultation path across it in the sky plane. In each of the 12 diagrams, the dashed lines, see the dashed line? The dashed lines indicate the geometrical occultation. The solid lines indicate the actual brightness as amended by diffraction effects. For the purpose of understanding the diffraction diagrams, it is helpful to think of the wavelength and distance as constant in all these diagrams, so that the different columns differ only due to the effect of asteroid diameter. Now, at the bottom is a kilometer scale, and I want to tell you that the kilometer scale is dependent upon the wavelength and the distance, and therefore it can't be extrapolated to other cases than presented here. The thing that can be extrapolated is the rho value as applied to all the diagrams. Please direct your attention to this left column with a rho value of 0.88. There's a strong central spike for each of these occultations with the exception of this one. It's attenuated greatly by an occultation across the short dimension of an elongated object. This central spike in these diagrams is a Poisson's spot caused by diffraction, and it must not be confused with the central spike seen in occultations by large bodies that have atmospheres, such as Titan and Triton and Pluto. These atmospheric central spikes are caused by refraction, not by diffraction. While looking at the patterns in the left column with rho of 0.88, imagine that you were observing an occultation by a small elongated object like Apophis with a rho value of 0.88, which is realistic for Apophis. You might expect to record a strong central diffraction spike. If the spike fails to show up, its absence suggests that you have recorded an occultation like this one, across the waist of the elongated object. Notice that for any occultation with a rho of 0.88, the brightness does not drop to 0 at the nadir of the event. Now please direct your attention to the top two rows together. The point of these two rows is to contrast or to compare the effects of the diffraction pattern for objects with very different shapes. Although you might think that these are both square, the occultation path across a square from the faces of a square versus the diagonals actually makes the effective shape very different. And I want to point out that the diffraction effects are very similar. And this shows that asteroids of very different shapes can have very similar diffraction patterns at all values of rho. Now, if you'll please direct your attention to the bottom row, this shows a diametric occultation by a circular body. Note that this is the only configuration in which a strong central diffraction spike occurs at any diameter. The diffraction spike becomes progressively narrower at large values of rho, so that in actual practice, it becomes more difficult to detect. The bottom right diagram shows that the detection of a Poisson spot can require good luck. I'd like you to imagine an observer's cord that passes close to that diffraction spike. You see, he's not going to see any brightening, even if he's very close to the center line. Consequently, he must be right on the center line to detect the Poisson spot. It's incidentally, for a perfectly spherical object and a perfectly diametric occultation of that object, the Poisson spot has a peak brightness at any wavelength that's exactly equal to the unocculted brightness. I haven't mentioned the diffraction brightness peaks that are immediately before and after the geometric occultation. Notice that they present in every one of the 12 diagrams. Notice that they all peak at approximately the same distance outside the geometric occultation. They are outside the geometric occultation, and by approximately the same distance, a wavelength dependent distance. Now please direct your attention to the columns on the right, the two columns on the right. And I want to point out to you that these have rounded bottoms. Most of them have rounded bottoms. That's a feature of the diffraction effect. And finally, I want to point out something that you may not have noticed yet. In all 12 diagrams, the disappearances and reappearances are not abrupt, but are gradual. This is despite the computation of the diagrams in which the star was considered to be a point source. Of course, your ability to record the gradual nature of the dimming and brightening depends on the frame rate you use. Clearly, a high frame rate may assist in recording diffraction features. So if you're going to use diffraction features to help you identify an occultation when you know that the occultation is not going to look like that of a main belt asteroid, it helps to have a high frame rate. This slide shows a compilation of some data about most of the observed occultations and appulses by Apophis in 2021. If you look at the second column from the right, over here, second column from the right, those are the rho values of those events. Notice that the first 6 events, the rho value was intermediate between that of the first 2 columns of the previous slide. For the final 2 events of this slide, the rho values were similar, 0.85 and 1.1, similar to the rho values in the first column on the previous slide. Diffraction explains the non-zero event bottom in Steve Conard's asteroidal moon detection. It's also a possible cause of the increased number of points of intermediate brightness. Diffraction appears to me to be unlikely to be the explanation of the central peak in IDA's near centerline recording of a Phaethon occultation. The rho value was 22, so any diffraction spike should be very narrow. As I pointed out when displaying the diffraction diagrams 3 slides previously, even a grazing pass through the bottom of the central spike will be quite narrow, not wide as the central spike is here. Note that Phaethon's diameter is about 15 times as great as that of Apophis. So if the two are at the same distance, Phaethon's mid-occultation spike will be much narrower than that of Apophis. This central spike remains a mystery to me. Diffraction, I believe, explains the non-zero event bottoms in these 3 events recorded at Oakdale, Louisiana in the first Apophis occultation. And in Dunham's light curve on the left, I think that this peak is suggestive of a diffraction effect as he got part of the central Poisson spot, because with Apophis, that Poisson spot is broad. Even with the Richard Nugent's slide, his middle frame of the 3 was slightly brighter than the other 2. Makes you wonder whether there might have been something there. And of course, this event is so brief, a single frame, and remarkably far from a complete disappearance. The rho value of this event was 2.4. With Kai Gatros' recording of the Apophis event, remember this is at 100 frames a second, diffraction explains the rounded bottom. Diffraction explains the peaks before and after Piot's recognized event. And as I said, notice that the diffraction peaks before and after it are a frame or 2 away from the actual geometric occultation. We have long thought of an asteroid shadow as something like that diagrammed here. Again, this is the Oakdale Google Earth map with the chords at Oakdale. Here we see the shadow of Apophis about to encroach, coming southeastward, about to encroach upon the 3 positive sites. Actually, the shadow was something like this, with a bright center that appears to have been detected by the Dunhams near the center line. And a bright external ring that causes the brightness peaks immediately before and after geometric occultation. These brightness peaks before and after the event were obscured by the low signal to noise ratios associated with the small telescopes used for these observations. With this slide, I have drawn 3 bright green lines across the shadow in order to emphasize the difference in the light curves that 3 observers might see due to diffraction effects. The observer at the southwest of these 3 lines would see along chord number 1. He would first detect a brightening, then a dimming, then a brightening, then a dimming, and then a brightening again before getting back to baseline. The observer in the middle chord here along 2 would see a brightening and then a dimming, no Poisson spot, then another brightening before getting to baseline again. This is the kind of observation that Kai Gatros seems to have had. While an observer at 3 has an especially interesting chord, and the reason is, since he's not getting into the nadir of the diffraction effect, he's just grazing along the external brightening, and he might have a protracted brightening without even realizing that he's witnessed an occultation at the edge of an occultation shadow. Now for a look at diffraction effects from a different point of view. This slide is copied from a 2020 article by Siraj and Loeb, in which they discuss the possibility of detecting free interstellar planets by the occultation of faint stars. Note that they say that the rho values of such occultations are very small, similar to those we see with near-Earth asteroids. Accordingly, the slide shows very prominent diffraction effects as the faint gray lines, not the red lines. The numbers on the abscissa at the bottom are units of camera frame duration, not time per se and not distance. The red lines show the brightness that the camera would record as its exposure spans the part of the diffraction pattern that occurs during that exposure. In every camera frame, this brightness amounts to the area under the part of the diffraction curve exposed during that frame. The key point here is that for a rapidly changing diffraction pattern, a camera frame rate may be too slow to detect the finer diffraction-related features of the occultation because of the camera's averaging effect. For example, if you look at the lower right, the diffraction nadir is at 0.3 of the unocculted brightness, 30% of the unocculted brightness. But the camera records it in the integrated light value at about 60%, 0.6 times the unocculted brightness. So the slow camera rate is going to mask the diffraction effects. If you look at the lower right panel, this guy might be on the center line, but you see how the camera rate masks the detection of the Poisson spot. So he doesn't really detect one. So it appears that fast frame rates are beneficial in elucidating the diffraction patterns of these very brief events. This again is the table of most of the occultations by Apophis in 2021. And I want you to notice that the very last event is in 2022. And the star diameter in that event was 0.379, about 0.38, 3/8 of a milliarc second. Compare that to the others. Most of them were like 0.02 and so on. The second largest one was this one, which is less than half of that here. And so I just want to say that star diameter effects can be pretty important. This diagram represents star diameters superimposed on Apophis's approximate size for the purpose of explanation. It illustrates three possible vertical paths along which the asteroid might cross the star. The actual shape of this asteroid is not well known, but it is thought to be elongated in roughly this proportion. Also, the particular presentation of the asteroid's contour at the time of the appulse was unknown. The sizes of the star and asteroid here represent the actual dimensions given in standard source material. The greatest top to bottom distance across the asteroid is 0.873 milliarc seconds, a value specified by the Horizons ephemeris in the appulse of April 9, 2022. The star diameter is 0.379 milliarc seconds as specified by Gaia in DR3. The spacing of the star figures in each of the vertical rows is the distance of a single camera frame time at the frame rate I used in that observation. The frame rate was 380 frames per second. In the central row of stars, it shows a scenario in which there would be 4 frames in which the star is completely occulted, with at least one additional frame of intermediate brightness at the beginning and the end. You may, if you think about it carefully, you'll see that there are probably at least 2 frames at the beginning and the end, and a trace of a third frame, perhaps. Notice that this, I want to say that, notice that this is not due to an abrupt disappearance or reappearance during a single frame's exposure. So the cause of the intermediate frame brightnesses is very different from what we see with an abrupt event. That's due to the large star size. The left row shows a scenario similar to that in the middle, except there is only 3 frames of a fully occulted brightness, again with 1 to 3 frames of intermediate brightness. In contrast, on the right, we have an occultation which is partial by virtue of the large star size. Now, if the star were a point source, you see this would be a complete occultation. However, due to the large star sizes, with this event, there's not only an incomplete occultation, but there are at least 3 frames of intermediate brightness both before and after the central event. One of the important aspects of these scenarios is the effect that the large stellar size has upon the diffraction pattern that an observer would record. Notice that when one part of the star is at a point which it should be contributing to a central brightness spike, for example, here, let's take this star right here, that image. This edge of the star is near the edge of the asteroid. It should be contributing to a central brightness spike. This edge of the star is over here near it's contributing its brightness to a nadir. So the point is that the star is not a point source. And it's likely that these competing effects of the diffraction pattern would result in the elimination of the Poisson spot. I think that the overall effect here of the large stellar size is similar to that of the relatively slow frame rate effect illustrated 2 slides ago. At the risk of being very redundant, I want to say that the significance of the effect of star diameter as illustrated here is related to the very small size of the asteroid. For large asteroids, the effect is generally considered to be minuscule. The top half of this slide shows the likely timing uncertainties an observer might experience due to the combined effects of diffraction, frame duration, and stellar size. For Apophis at the top, they may add together to make up a significant fraction of a path width. The bottom half of this slide shows the same effects as they relate to an ordinary main belt asteroid, Barbara, which is about 45 kilometers in diameter. Notice a tiny dot at the lower left, way down here. That is Apophis at the same scale as Barbara. The effect of star diameter that I have been describing is of the same magnitude for all occultation observations. That is, star diameter effects are not related to asteroid size. The effects of frame duration are also unrelated to asteroid size, except insofar as they affect the recording of diffraction features. Diffraction effects actually decrease with large asteroid size. So the summed effect of all these 3 phenomena is probably slightly less for large asteroids than it is for small ones. I don't mean proportionally less, I mean absolutely less. The uncertainty zone that they cause around a main belt asteroid like Barbara is less than 1 pixel in this diagram. That is why I have been speaking about these effects in regard to near-Earth asteroids. The effects of diffraction and probably the effects of star diameter and frame rate will affect occultation light curves of some trans-Neptunian objects in the same manner by which they affect near-Earth asteroids. This is because their distances are great and the diameters of many of them are small. This table lists 3 large TNOs, Pluto, Quaoar, and Haumea, and their respective moons with the rho values in the last column on the right. Over here we have the rho values. Of course, Charon is pretty big. It has a rho value of about 16. But look at the other 4 moons of Pluto, Styx, Nix, Kerberos, and Hydra, and look at their rho values. They're tiny. In 2009, a prediction was made that Pluto's moon Hydra would occult a star as seen from my home. And I set up a 14-inch telescope in my backyard and had no difficulty imaging the star, which was a lot brighter than Pluto. I interpreted my observation as a miss. However, in looking at the rho value of 0.5, I now wonder whether I could have identified a positive observation even if an occultation occurred. Notice that Weywatt's rho value is 1.9. This object is a good candidate for the display of prominent diffraction effects, as well as star diameter effects and frame rate effects. And I'd like to open it for discussion.
So Roger, if I may, I'd like to share my screen just momentarily.
Fine with me.
Okay, you have to allow me to share.
Oh, let's see. It says one can share at a time. And oh, let's see. There you go. Now you should be able to. You should be able to share now.
So what I'm putting up is a solution to an occultation that I had recently called PIOF. And I had a gradual disappearance and reappearance, you know, with a couple of 3 points in each. And I just wanted to point out that PIO does have a diffraction tool and a penumbral occultation tool available to fit those points. So you may want to go back and try to fit the light curves you were showing us to using the diffraction tool. It's pretty easy and pretty handy, and and I can get pretty good results with it depending on the event. So just thought I'd point that out.
Okay, thank you for pointing that out. Good.
Let me just say, well, first of all, Roger, what a terrific presentation. It's clarified some things. I thought I knew a lot about this subject. I have to say that although PIO does have this ability to model a diffraction curve, I don't know what rho value I used, and it is fixed. And it's pretty clear that I need to go back and take a look at that. You know, I used a fixed value, it was probably somewhere around 2 or so, because I wanted to pre-calculate things so it didn't take forever to do a fit. But your talk has motivated me to look into that in much more detail. Thank you.
Any other comments? Okay,
Yeah, I've got observations of Waywat, which are just sitting on my computer, thinking I probably had a miss, but now you're causing me to maybe go back and take another look.
yeah, and remember that with a rho value of 1.9 for Waywat, you may just, if you're on the edge of that occultation, you may just see a brightening, you know. And I showed that with one of the chords, how that could happen, and due to diffraction effects. So just be alert to any change in your light curve. The point, really the point of the whole discussion was that these observations of very well, I call them brief events, but really it's a matter of the Fresnel length. You know, these observations do not look like traditional occultation light curves. So, you know, we can identify them sometimes, I think, if we have a good signal to noise ratio, by the features that I pointed out. You know?
Yeah. Well, I know Kirk Bender submitted. Sorry.
One of the challenges with this effect is that if you've got a brightening effect or markedly reduced event brightness, then you've got a serious challenge to distinguish an event from noise if you're just a single chord. I mean, effectively, the diffraction effects that Roger's been talking about is great when you've got a couple of observers where you can tie things together. But if you've just got a single chord with a brightening rather than a drop in brightness, you're not going to be able to say that's definitely an occultation. It's a problem issue, but you've got to have some basis for saying it's an occultation. And a little drop rather than a big drop, a little drop that's buried in the noise without sharp edges, is a challenge to say with a single chord that was definitely an occultation.
Well, fortunately, Kirk Bender and I often are set up only a few miles apart, and so I have relied on him to try and confirm, even though it's, I don't know, it doesn't seem to be in the software, but you know, whether we both have events or whether we both don't.
Yeah, I think a confirmatory chord would be very useful to help in identifying a diffracted light curve. But I would think that we would be sensitive to the possibility now that we know what diffracted light curves look like, you know.
Well, since we know which objects presumably have these small diameters and big diffraction effects, we
should be looking for them.
Yeah, we should look for them. And also, I think that'll help with some of Dave Harold's concerns that you wouldn't want to be looking for exaggerated effects on some big asteroid and, you know, call it diffraction when it's really noise.
All right.